So hi everyone, welcome to this session on NIZKs and SNARKs. So I'm Daniel and I'm co-chairing this session with Takashi. And we're going to have, hi. And we're going to have 5 very nice papers. And I suggest that we directly jump into the presentations. So the first paper is Lunar, a toolbox for more efficient, universal and updatable zkSNARKs and commit and proof extensions. And the talk will be given by Anaïs, and I would suggest to just jump into it.
Can you see the slides?
Yes.
Okay, nice. So thanks for having me here. I am Anaïs Querol, and I'm going to present Lunar. This is joint work with Matteo Campanelli, Antonio Faonio, Dario Fiore, and Hadrián Rodríguez. So this belongs to the area of zero-knowledge SNARKs, which basically focus on the problem of showing that a claim is true without showing any more than the fact that the claim is true. So we don't filter any more information. So with universal zkSNARKs, we can have it by having a one-time setup for any bounded relation that fits within some bounds. And with updatability, we can have a number of active participants that collaborate on the randomness and thus reducing trust requirements. So this has been a very active area of research recently, starting from Groth et al. With the quadratic size SRS, and then some linear size SRS, among which Lunar is located. And now if we look at some of our contributions, what we give is a family of efficient universal updatable zkSNARKs and CP-SNARKs versions, and also the first, to the best of our knowledge, compiler to this type of CP-SNARKs. We also give a more general type of information theoretic object that we call a PHP. And we make our compilation through efficient blocks that are CP-SNARKs as opposed to polynomial commitments. We give the notion of somewhat hiding commitments, which means that we are not using fully hiding commitments in order to achieve zero knowledge. And we also give a new shorter constraint system that we call A1CS Lite, for which we build our constructions together with A1CS. So this table just shows some numbers on efficiency for constant proof candidates, but feel free to look into the paper for more details, because this is only for one of the members of this family. So now if we look at the first type of the compilation, we wanted to generalize Planck's and Marlin's approach, which are IOP-based type of information theoretic object with some limitations, in the sense that some notions of zero knowledge were lacking in the abstraction, and the type of point evaluations that are performed in the verifier side had a vast impact on proof length. And this first approach was then compiled with using polynomial commitments, but this implies that some optimizations deviate from the abstraction, and we wanted to address this problem by using modular and then interoperable CP-SNARKs as our blocks to do this compilation. So if we look now at what is a PHP, so this is very similar from a high level to ASPs and ILDPs. Essentially, you have an offline phase where the indexer encodes the relation polynomials and the verifier has oracle access to them. And then in the online phase, prover and verifier talk with each other, prover sending oracle polynomials, verifier answering with some randomness. And then at the end of these rounds, the verifier performs some checks of these degree bounds and some polynomial equations. Now, if we look at the compiler to SNARKs, we will see this key generation algorithm that basically corresponds to this one-time setup for a number of relations that fit within some bounds. And then the derivation algorithm specializes in these SRS for a specific relation, which basically consists on committing to the polynomials that are output by this indexer. Then the prover for each of the rounds of the PHP will commit to the polynomials that are output by this PHP prover, and giving a proof of opening of those polynomials, and then providing a proof that the PHP verifier would accept. And then the verifier simply takes those proofs and verifies the PHP side, meaning these degree checks and polynomial equations, and proves as well and verifies as well the knowledge of the opening of those polynomials. So if you look at here, those types, we have a type-based commitment scheme for two types, relation types, which are these white ones, which correspond to relation polynomials. And this is non-hiding commitments. This is a deterministic commitment scheme, because this is only public information, so we don't care about that. And we also have something called somewhat hiding commitments, which are commitments that filter up to one evaluation at a random point, which means that we are not using fully hiding commitments in order to achieve zero knowledge. And this is very interesting for efficiency. So if you look at the main building blocks that we have for our compiler, you will see then that the CP-PHP is also formed by two other building blocks, one for polynomial equations and another one for proving degree bounds of these committed polynomials. And for each of those, we have a number of instantiations of these blocks with different properties. For instance, for the opening of a polynomial in the PKE assumption, we give a novel batching technique for L commitments using only one group element. For polynomial equations, we have a novel empty proof in the case that you can express that equation as a product of two committed polynomials, quadratic equations. And also for the degree, we use this commitment to the shifted polynomial. And if you can express that as a quadratic equation, again, you can have empty proof as well for the degree. So in this picture, I just wanted to show what are all the possible combinations of these blocks in order to produce all of the members of this family that I'm talking about. And just to name a few, I'm giving here three of our constructions. We have Lunar Light for this R1CS Light constraint system, our Lunar 1CS fast and short, and Lunar 1CS short VK for normal R1CS. So if you want more details, feel free to watch the video or refer to the paper. So if you have any more questions, I'll be happy to answer. Thank you.
Thanks a lot, Anaïs, for this nice talk. I forgot to mention, so if you feel comfortable, just unmute you if you have any questions. So I don't see anyone on Zulip or the Zoom chat. So anyone who has a question?
Yeah, I'm not receiving questions either, I think.
Okay, so I have a question.
Okay.
So do you think that this notion of somewhat hiding commitments kind of like going to be a more generic thing that you can use in different application scenarios, or is this very specific to these types of systems?
So I would say we can apply that to other systems as well, as long as all of the blocks that are involved, oops, I hear some noise, have some features. So the somewhat hiding commitments is not like the only requirement that makes all of it work, because we also have other notions of bounded zero knowledge and leaky CP-SNARKs. So altogether, with all those ingredients, we can have fully zero knowledge SNARKs. So if you remove some of these pieces, then perhaps you need other type of assumptions on those commitments. But as long as you can have the equivalent notions for other constructions, I guess you can also use them for others.
Okay, thanks.
No problem.
Okay.
So yes, we move on.
Move on to the next talk. So the next talk is Gentry-Wichs is tied, a falsifiable non-adaptively sound SNARK by Helger Lipmaa and Kateryna Pavlyk. And I believe Helga will give a talk. I cannot hear you. Please unmute.
Yeah, can you hear me now?
Yes.
And you can see my slides. So
yes.
Very good, thank you. Yeah, this paper is called Gentry-Wichs is tied, a falsifiable non-adaptively sound SNARK. It's co-authored with Kateryna Pavlyk, and we both work at Simula UIB in Norway. And like when I was recording, I was quite sick. I'm still a bit of like without voice, but I hope it will be okay. So let me try to first talk about our model. So Anaïs already introduced zero knowledge. So, but I want to be a bit more precise about the model that we are working in. So the most standard model in the case of non-interactive zero knowledge proofs is in the CRS. Well, it is in the CRS model. Third party who and then you have a prover and verifier, and then the trusted third party is generating a CRS, sending it to both the prover and the verifier, and after seeing the CRS, the prover can choose some input, and the private witness send the input over to the verifier, and then accompany it with a zero knowledge proof that this input belongs to some language. And this moniker SNARG means succinct non-interactive arguments. And the first word succinct basically means that the proof has to be succinct. So this is the common case, or so-called adaptive case, where the input can depend on the CRS. And just once more, to give a bit of motivation why we are working on this problem, is that there's a lot of money in the area of SNARKs, real money. There's hundreds of papers in top conferences used prominently in the real life. But then if you look at any SNARK paper written ever, it has the following claim. Our construction is based on non-falsifiable assumptions due to the impossibility result of Gentry-Wichs. And this claim is something we are interested in. So what does Gentry-Wichs say is that there are basically 4 different properties that you cannot achieve at the same time in non-interactive zero knowledge. So you cannot achieve adaptive soundness, succinct arguments, you cannot handle hard languages, and you cannot have it under falsifiable assumptions. There are actually several impossibility results in this area, but Gentry-Wichs is the most famous. And then now, when you look at this impossibility result, the question is that we cannot get all 4 at the same time, but can we get any 3? And in most of the combinations, this was well known before. For example, if you don't care about succinctness, then this has been known for around 30 years, at least, by Feiger, Lapidoth, and Shamir. If you don't care about hard languages, then you can just construct something for the complexity class P. And for this, we have delegation schemes. And if you don't care about falsifiable assumptions, then we have SNARKs. So our paper fills the gap. We show that we can get the other 3 properties if we don't care about adaptive soundness. So just to explain why any of those properties is needed, the succinctness is basically the efficiency property saying that the communication is small and the verification is efficient. Hard languages, that's an expressivity property. Basically means that you can handle all NP languages, do something that is actually non-trivial. Adaptive soundness is a security property, so it means that soundness holds even if the input can depend on the CRS. And now, if you have, so on top of it, you have like this 4th property, which is falsifiable assumptions, and which is basically you can efficiently check if an assumption was broken or not. And in practice, it seems that people really care about the first 3 assumptions, but not about the last assumption, but or last property. I would also argue that the last property is very important, because if you are basing your system on very complicated, hard to believe assumptions, then your scheme might be broken at some moment. But also, I think it's just a theoretically interesting question to see whether actually this impossibility result is tight. So yeah, the first 3 properties are needed to get this 2 billion for your scheme. And the 4th property is needed to to kind of get an assurance that your scheme is still there in 5 years. So what is this non-adaptive soundness? So in the case of non-adaptive soundness, you kind of assume that the input does not depend on the CRS. So in the security game, you can model it so that you first let the prover to choose the input and the witness, and then generate the CRS. You don't have to do it that way. It doesn't have to be like a temporal dependency. You just have to assume that the input does not depend on the CRS. If it can depend on the CRS, you don't have the security guarantee. And you still have a succinct proof. And this is non-adaptive soundness. So what are our results? First of all, like I said, we breached this gap. We propose the first falsifiable non-adaptively sound SNARK for MP. It is succinct. So while it is a theoretically interesting question, I just want to emphasize that we actually get something that is fairly practical. So the length of the argument is 9 elements from G1 and 5 from G2. We work in pairing phase setting. And this closes the gap in Gentry-Wichs. And then the paper delves into many other additional properties. So for example, we also show that this new SNARK, in addition of being non-adaptively sound under falsifiable assumptions, it's also non-adaptively knowledge sound in the algebraic group model. And it's subversion zero knowledge under a non-falsifiable assumption. And in both of those cases, it's kind of a known that you really need a non-falsifiable assumption. There's a later talk in this section about Vegoffs by Arne and Tobias, etc., where we try to actually work on this. And the paper has two major building blocks. One of them is so-called bilateral subspace quasi-adaptive NIZK, and another one is functional, somewhat statistically binding commitment scheme. And in addition, we also get new results about the bilateral subspace NIZK. And just one more slide, or sorry, 2 slides. So one of them is like more conceptual. How we get what we get is that we don't have a real extraction in the scheme. We have local extraction. So basically, we let adversary to guess which, sorry, not the adversary, but we let the reduction to guess which gate was miscomputed by the adversary. We abort if the guess was wrong. And then we prepare the CRS so that one can efficiently extract a succinct local witness showing that this concrete gate was miscomputed. And then we reduce to soundness to a falsifiable assumption that uses only this succinct local witness. And then there are 2 previous papers. One of them is by Daza, etc., from PKC 2019. And another one is by Fauzi, myself, Pintado, and Janosim from this year, where we use local extraction from non-succinct commitment. So in those papers, we got adaptive soundness, but we had a long commitment. But we still worked under falsifiable assumptions. And here we turn it around. We get non-adaptive soundness, but we have succinct commitment. So I think that is now really the last line. So I'm trying to explain like how this soundness proof works. So basically, it's written down in a linear way. In the actual paper, you have security games, but the idea is that you have adversary to commit to the witness by using the succinct, this functional SSP commitment. Then you guess the gate where the adversary cheats. Then you force adversary to fix input, and you can do it because you are in non-adaptive case. And then after that, you modify the CRS to allow local extraction of this concrete gate. Then you obtain the argument from adversary because input was fixed. This miscomputed gate number did not change. Then you extract local witness from the commitment. You reject if guess was wrong. This means that you have a security loss of like the number of gates times. And since we did not reject, and we have non-adaptive soundness, the adversary input does not depend on the CRS. Hence, the gate where adversary cheated does not depend on the CRS. It's still the same gate. We have a local witness that this gate was miscomputed, and we use it in a reduction to a falsifiable assumption. And thus, we get the non-adaptive soundness. And again, to not contradict Gentry-Wichs, non-adaptivity is needed. While in those two previous papers, they got adaptive soundness, but they had non-substance commitment. So thank you all. And I don't know if you have any questions. Thank you.
Thank you, Helger. So do you have any question? So I don't see any question in the chat. So I have one quick question. So as far as I know, the Gentry-Wichs impossibility result considers SNARKs whose CR generation efficiency is independent of the statement length. Sorry. Can you mute? Oh, sorry. so as far as I know, the Gentry-Wichs considers SNARK with CR generation efficiency independent of the statement length and witness length. And my question is if your construction satisfies this property.
No, we actually have a long CRS, and the CRS depends on the language. So it depends on the language. So it's for circuits. The CRS depends on the circuits. I think it's a very interesting question to see if we can actually get the shorter CRS.
Yeah, so in that case, it is correct that it may be possible to extend Gentry-Wichs impossibility result to non-adaptive soundness if we require circuit independent CRS generation.
It might be. I don't know.
Okay.
So there are. Like I didn't mention during the talk, but the construction definitely has some limitations. So the CRS is long, and the CRS depends on the input. The problem is that if you look at the current constructions of SNARKs, where the CRS does not depend on the input, so universal SNARKs, they actually all efficient ones, all efficient constructions work in the random oracle model. And getting rid of the random oracle model, even just like, let's say, have an efficient construction of universal SNARK where you can rely on the knowledge assumptions, but you don't have random oracle model. I think even this is an open question. There are somewhat non-efficient constructions, but at least this is my knowledge. Maybe there's some recent paper that does it.
I see. Thank you so much. So thank you, Helger. We'll move on to the next talk.
Yes, Helga, I had one more question. So, is it possible?
Yeah, go on.
So, I mean, would non-adaptive soundness be a notion that's reasonable for the applications that you used as a motivation?
Well, we really don't have an application in mind. So to be completely honest, we just started to tinker with previous constructions, to see whether we can improve on it, and at some point we realized that we can get this trade-off. But it's a very good question, because basically, like on the slide, I was showing that the input has to be chosen before CRS was generated, but this is actually not the case. So I think if you have like some kind of a restricted application where cheating maybe just doesn't make sense if your input depends on the CRS, then I think it's fine. But I'm not really sure what would that application be. I'm quite interested in the question, so we can talk later.
Yeah. Okay. Thanks.
Thanks.
Okay, then let's move on to the next paper. But as far as I see, there is no author online, right? Is there anyone for the third paper? So otherwise, I would suggest that we postpone this paper and then see later if someone is here, and just move on to the next one.
Sure.
Yeah,
then,
I guess that's
then
me.
we
Yeah?
come on the next one. And then the next talk is Snarky Ceremonies by Jano Sim, Mark Karkovets, Mikhail Varkov, Mary Mahler, and Jano will give a talk.
Yeah, I hope you see my screen.
Yes.
All right, great. So thank you for the introduction. So you already heard quite a bit about zkSNARKs. So these are non-interactive arguments with knowledge soundness, zero knowledge, and succinctness. And one of the most efficient zkSNARK was proposed by Jens Groth in 2016. And it has a lot of nice properties. It has the smallest proof, the fastest verifier. It's very widely deployed in practice. And it has lots of other nice properties like proof aggregation and weak form of simulation extractability and so on. And it also works in this common reference string model that you just saw. So at the center of it, you have this trusted party. You have a prover and a verifier. Prover knows the statement and the witness, and verifier knows just the statement. And then this trusted party will give a common reference string, which is a bit string from a very specific distribution to the prover and verifier. And then prover can use this to construct an argument. And verifier will either accept or reject this. However, this trusted party also holds a secret trapdoor, which is basically a key that if you hold it, you can easily cheat in the proof. So if this trusted party is actually a bit malicious, then the whole system collapses. So in response to that, there was a proposal for updatable reference string. So in this model, you have a bunch of parties, and they update the CRS one by one. And the final CRS is now secure, or in other words, the secret key has not been leaked if at least one of the parties is honest. Unfortunately, the SNARKs in this updatable reference string model are a bit less efficient. Actually, Bowie, Gabbison, and Myers also proposed an updatability ceremony for the Groth16 SNARK. The difference here is that this ceremony protocol works in two phases. So the first phase looks kind of similar. You have a bunch of parties updating, and you obtain what we call a universal CRS. So this is a CRS that's independent of the concrete relation that we're trying to prove. And then you have another phase which works slightly differently, which already depends on the relation, where again, everyone will update the CRS, and then you will obtain the final CRS that you can actually use. And in either of the phases, you now need one honest party in order to get security. This protocol has been very widely used in practice in all those blockchain projects and so on, but it also has a slight theoretical problem, at least, that it uses a random beacon. So what's a random beacon? It's basically some source of randomness that periodically produces you unpredictable random numbers. So at some point it will produce one number, and in another point you might want another complete unpredictable random number, and so on. And at least if you want to construct provably secure random beacons, then it's far from trivial how to construct them. So ideally, we would not like to have this at the center of our protocol at all. And the way it's actually used in this protocol is that at the end of each updating phase, you apply a random beacon output to somehow randomize the CRS. So what are our contributions? Firstly, we propose a formal model for these types of multi-phase ceremony protocols that uses thought. And this can be seen as a generalization of the updatability model, or actually, you can actually restrict our model precisely to updatability. Then we propose a variation of the Bowie-Gaddison-Myers protocol, which doesn't use random beacon at all. And finally, we give a proof of security in our new ceremony model. And this proof of security uses both algebraic group model and random oracle model. And yeah, it's quite a technical proof, but it turns out that if you cut away this random beacon from Bowie-Gaddison-Myers ceremony, then it's still actually secure. And moreover, our security proof also applies to current executions of ceremony protocols that are already used in practice. So even if they have an insecure random beacon, then they are actually still safe. And that's it. Thank you for listening.
Thank you, Jenna. So do you have any question? So if you have a question, please write at the Drip chat or Zoom chat. There's no question so far. So I have one question. So I'm wondering if this can be seen as a special case of multi-party computation, or there's any essential difference?
Yeah, it can be seen as a special case of multi-party computation. I mean, in general, you can use multi-party computation to always generate this common reference string. The problem is that in many applications, you want a huge number of parties to participate in this multi-party computation, and you also want, or also this common reference string is very large. So often, general multi-party computation protocols are not very efficient for this case. And also the nice property here is that you only need one honest party in each phase of the protocol. But in general, yes.
I see. So the problem is efficiency. Thank you. And
Yeah.
I found one question in the chat. How much stronger do you feel the random beacon model is than the random oracle model?
Well, the question is like, how do you construct a random beacon? Random oracle is very simple to obtain. You just, I mean, you pick a hash function that looks secure and you're kind of done. With random beacon, you know, there are some practical solutions like, for example, you take a blockchain block that was proposed, I don't know, 10 blocks ago in Bitcoin, and then you hash it and you kind of claim that this is now the output of your random beacon. Can you prove that this is actually secure? I mean, maybe you can somehow, but I'm not sure. But actual constructions of random beacons are a lot more complicated.
Thanks. Is there any other question? So if there are no question, let's move to the next talk. Thank you, Jano.
Thank you.
Okay, then let's move on to the next talk. So the next talk is on efficient NIZKs for algebraic set, and Roberto will give the talk. So please go ahead.
Yes, I guess you can see my slide.
Yes.
Okay, so I'm going to present the feature NIZKs for algebraic sets. This is a joint work with Geoffroy Couteau, Helger Lipmaa, and Arne Tobias Odegaard. We are talking here about non-interactive zero-knowledge or short-tree NIZK argument. They are protocol engaged by these two parties, Alice the prover and Bob the verifier, and Alice wants to convince Bob that she knows a witness W for a statement X. As before, we require that only one message is sent by the prover to the verifier, which without an interaction is only to output accept or reject. And different to other previous cases we have seen in this section, here we don't require that the proof is succinct. Also, we must suppose the existence of this trusted third party that computes and makes available to both prover and verifier a CRS. And those protocol has to be complete in the sense that honest provers always convinces the verifier, sound in the sense that malicious prover cannot convince the verifier, and zero knowledge in the sense that the verifier cannot learn anything about the witness. In our paper, we present a new method to build NIZKs. So I'm start with an overview of the existing NIZK construction, compare them in terms of efficiency, expressivity, and security, and at the end, I also compare them with our NIZK. The first NIZK construction was due to Fiat and Shamir. They performed very good in terms of efficiency and expressivity, but they are only proven to be secure in the random oracle model. Then after a while, GroupSci NIZK came. They were the first NIZKs proven secure under standard cryptographic assumption. However, they have several limitations. So often they are just not efficient enough for many applications. And they are also restricted to, they are also defined only for pairing product equation, which means that in order to have a GroupSci NIZK for a specific application, one must also must first find a representation of a given problem as a set of pairing product equation. And then 1 year ago, Couteau and Hartmann developed a new way to build NIZKs. And those NIZKs have some very appealing features, such as efficiency comparable to Fiat-Shamir NIZKs for some application, but they also have some critical limitations. So they are defined only for algebraic languages, which is in principle a class of languages even more restricted than pairing product equation. And they are secure under a novel assumption, which was not enough analyzed. Lastly, our NIZK built on top of CH20 results solved some of the previous limitations. So first, we slightly improve efficiency for some application, but at the same time, we widely enlarge the class of the supported languages considered algebraic sets, and we also relied on better assumptions. So an algebraic set is defined by a finite number of polynomials over a finite file as the set of common roots of those polynomials. We also use public key linearly homomorphic encryption scheme. And we define our languages as the set of encryption of elements in the algebraic set. Our main contribution is a general framework to define a NIZK for those languages. The framework is divided in 2 steps. The first step is to find a base of the algebraic set. This is done considering the algebraic set as an ideal in the polynomial ring. So we run an algorithm to find a good basis of the algebraic set. This algorithm has to be run only once. And I want to point out that this is just not a cryptographic problem. Many solutions are known that give like satisfactory result. So once we have this language defined in terms of the basis of the algebraic set, the second point is to build a NIZK for those languages. And this is our main technical contribution. I just want to point out that from the high-level description to the NIZK, this process is almost automatic in our paper, particularly doesn't require work from a dedicated expertise, which was not the case for GroupSci NIZKs and CH20 NIZKs. To show the goodness of our method, we have some application. So we have the best NIZKs for set membership. Also to prove that the points belong to an elliptic curve, which is an application required in blockchains and cryptocurrency. And we have also the best NIZKs for several circuit satisfiability problems, such as Boolean circuits and R1CS. But we believe that the best part of our paper is the framework itself. And we believe that as it was the case for GroupSci, many applications will come in the future. So thanks for the attention. And we also have the full version on ePrint with more details.
Thanks a lot, Roberto. Any questions from the audience? I do not see any questions in Suri or Zoom. So I think that's a really nice paper. So I just have one question. So, I mean, so do you think that this is kind of like already optimal what you're doing with this algebraic set representation, or do you see any path towards, I mean, improving efficiency or do even better?
Actually, I don't know. I think it's like to improve efficiency, one must really like found some better representation of the given problem. So I think it's mostly depend on the first step. If you can find like better efficiency, I think the second step is almost optimal, but that's only my intuition.
Okay, sure, thanks. So I just checked. Any other question?
So I have one quick question.
Yes.
So I believe the gross high is already somewhat efficient. So I'm wondering, so is there any concrete comparison of the efficiency between your protocol and the gross high?
Yes, we have several tables of comparison in which we show that we are more efficient than the group size. I think for we were like 20 to 30% more efficient. But also like for circuits, we are like a lot of efficiency is gained before our statement is only in one group, while with group size you have like to send the commitment in both groups. So already this gain a lot in efficiency.
I see. Thank you.
So I just checked, but I think that we have no one from the third paper here online. So I think it's in the middle of the night for them, so should be generous, I guess. Okay, then I think we're basically done. I want to thank all the people here in the session and all the speakers for the talks. I think we can close the session then. Thanks a lot, guys.
Thank you.